because gamma gamma prime is missing a lot of the.
Yes. So I think my first thought when we came here for this meeting is to Ricardo that has left us a few weeks ago. But anyway, we'll have time, I think, next day with Rico to celebrate, I mean, and okay, think about it. Okay, so thank you very much to Michael and Miriam for the nice talk. So very good introduction to the Pygmy Resonances. So I said not to why it doesn't change now.
Click on the slide again. Just on the slide.
Sorry?
Just click on the slide. Sometimes.
Yeah, good. but I know how to go back. Anyway, so just to be clear, we are dealing, when we talk about Pygmy resonance, of this kind of nuclei. I mean, the one with the rich neutron nuclei, to differentiate with the one of the neutron, the drip line, which will give up, I mean, show a neutron halo. So this is a kind of summary of the what I will talk this morning. So we know that they have a strong isoscalar component. In fact, we have seen that we can study it with several probes. Then we use it as it can be used at the low-lying dipole state as a good laboratory to study the interplay between isoscalars of vector mode. And although it has been studied for many years already, but we have a lot of open problems, and I will talk about that in the following, like collectivity, isoscalars of vector mix, role of deformation, and to clarify all these problems to get more, I mean, to understand better. This one is our, I think, in the future challenge for both the theory and experiment. Okay, we have already seen that you can investigate it experimentally with different probe, isovector probe, isoscalar probe. If I'm allowed, I will add another more experiment because I was involved. And this experiment done, I think, for a nucleus far from the stability line, with excited with isoscalar probe. This case was carbon-12. This was done in Catania with the Chimera apparatus. Okay, I will not go to the details, just to show that what was found is, I mean, close to the experiment quoted by Michael of Ireland and collaborators on nickel 68 plus gold at relativistic energy, which was done at GSI. Okay, so this is just to have a little bit more information. From the theoretical point of view, you have a macroscopic model. These were quoted by Miriam in course of Impressible 3-fluid model, where you use the Steinwell-Jensen model to describe the interaction between these 3 fluids, or you can have, which is the most popular view, you know, the dipole resonance, which are Pygmy resonance, which is the inert core which oscillate against the neutron skin. In this case, you apply the Goldhaber-Teller recipes, but of course you have a much better description of these low-lying states using the microscopic model, and you have a list of that. So you have RPA, which everybody knows, relativistic RPA, and the quasi-particle particle relativistic RPA. And there are these other three here, second RPA, subtracted second RBA, quasi-particle from model, relativistic quasi-particle time blocking approximation. And these are the one that are coupling the particle hole to more complex configuration. I will not go to describe all these things because each of them, I think, there will be argument of 3 talks in this week. So we will have all the details about this macroscopic model. Okay, so but you can get already some information just looking at this state with the, let's call it the simple RPA calculation. So these are the calculations done for the thin 132. This is the dipole state. So you have the isovector, which has this operator, this isovector response. This is the isoscalar response, and then you have here. I mean, for the region we are interested in, which is this one, we have here a lot of states, as we have, although these are above a neutron threshold, neutron emission threshold, but still you have several states. So one can try to put together in to bunch them and have a kind of try to extract a kind of general properties of these states. So a way to do that is to construct a single state which has an energy which is equal to the average value obtained by weighting the energy of the single state by their B1 value. This you can, from imposing that they exhaust the same fraction of energy weights rule, you can just get also the components of this new state. So if you look at this new state, and then you get the transition density from this state, which is states of this region. So you have this typical, I mean, shape that you have seen several times, where you have the proton-neutron transition density, which are in phase inside the nucleus, but on the surface, only the neutron is the one which gives a contribution, which implies that the isoscalar isovector transition density at the surface have the same strength, and this is the reason why you can excite them with the probe isoscalar and isovector probe. Okay. So all the theoretical calculations shown before have I mean, show this characteristic for the transition density for the states belonging to this lower energy region. Okay, it has been studied a lot since many years, as we have learned this morning from Michael and Miriam, but there are still some open problems. One is related to the fact whether they are collective or not. The other one is related to the fact where, I mean, the calculation, the experiment done for spherical deformed nuclei to see whether these low-lying states show some particular property as the deformed nuclei do for the giant resonance, for instance. And then we have to understand better the interplay between isoscalar and the isovector contribution. And I must add, for this just a personal point of view, until now I think we don't have a very satisfactory description of what is called splitting or PDR splitting. So, but I will have time just for these 2 points here. So this is a review paper that you can, of course, all of you know that. So they are due to collector single particle excitation. If you use the macroscopic model to describe the Pygmy resonance, this is implicit in the construction. In fact, yeah, you have this kind of a picture here that we have this the core and the neutron skin are oscillating one against the other one. But I think at the end of the week we'll probably learn that this picture is not really the correct one. But we will see. Probably just at the end of the day with Michael talk. So for the macroscopic model, we have to look, for instance, say on the simple RPA, let's say, and one to look at the number of particle holes that contribute to build these low-lying dipole states. But they have also looked at their coherent property, which is one of the fundamental property to establish whether a state is collected or not. So there have been several attempts to define the collectivity. One, for instance, that one by Breitner, Parr, and collaborating the collaborator Lanza. So they have in RPA calculation, you analyze the state of the low-lying states, and for a given state nu, then you construct this amplitude, which is the square of the x and y, which are the RPA amplitude, with this normalized condition, and then you can see what is the contribution in percentage of a particle of a single particle hole configuration. Another way to do that was done by Co and the collaborator, where they defined this index D, which is the ratio between the n star, which is the number of state which have this amplitude bigger or 1 over n pH, which is the total number of particle configuration, which means that D is 1 if all particle configuration contribute to the state with this condition, or it's 1 over n pH if only one particle configuration participates. So this is the two extreme case. This is just to count the number of particle holes that are participate to the construction of the. So here I will show some how in the case of the thin 132 that I showed before, these are the low-lying state. Then these are the composition. They are only two particle hole of protons and several neutrons. These are the contribution of each state, and these are the number or the percentage of neutron and proton for these low-lying states. It's the one that I showed before. These are the value of the parameter that I gave before. This you can compare with the giant dipole resonance, where you have a lot of much more states, and you have a stronger contribution from protons, which are the majority, 50%, 57% respect to the neutron one. So, but these are just the number of this. I say how we can see whether they are coherent or not. So one way we thought was to look at the B1, just write in terms of this elementary B1 for each particle hole. Contribution is written in terms of the x and y with this is the single particle transition. So here you have a plot as a function of a number of particle configuration for the isovector giant dipole resonance. So you see these are the contribution of particle hole of protons until here, and from here on we have the contribution of neutron, and this is the cumulative sum of the elementary B pH. You see they are, coherent in the sense that they have the same sign to the sum up. While if you go look at the state which corresponds to the PDR, this is for the case of nickel 68. So you see that there are a lot of cancellation between the particle, proton, and neutron. If you compare with the isoscalar contribution for the same state, the isoscalar response for the same the state and same energy, you see that they are actually coherent because this is sum up. This is just a comparison with 3- low line where you see we have very coherent state. So we can deduce from this analysis these are not collective state while the other one are collective. A similar analysis has been done by Xavi, Rocamazza, and collaborators. They just try to estimate the collectivity in terms of the reuse of the transition probability in Weisskopf unity. So you have this plot for 3 different nuclei, lead, thin, and nickel, with the 3 different Skirm force. And then you see that these are only a few units of Weisskopf to compare with the 60 units that you have for the giant dipole resonance. If you make a plot similar to what I've done before, in this case, they call it APH instead of B, and then you have a similar plot where you can, deduce that they are these states are not collective. Another way to look at in a global way at these properties is done by Reinhard and Nazarevich. They look at the correlation analysis, and they have this, they construct this energy averaged radial transition density in terms of the dipole form factor weighted with this Gaussian folded function. They plotted for T0 and T1, and then you can see here there is the projection on R and the energy excitation, and then you see that here you have a peak corresponding to the isoscalar giant dipole resonance, which shows that they are sum up, so they are collective. And the same you can see for the isovector giant dipole resonance, where you can see again a sign of a collectivity. If you go to the low line states, you have multinodal behavior, which is, suggests a weak collectivity of these states. So, but as we have learned this morning, and we will learn more in this afternoon and on Friday by Michael and Mark, it is you can also look at the experimental point of view. What about the try to see what is the content of the single particle state of these low line dipoles. So here is I just quoted this paper by Mike and the collaborator, which is DP reaction on lead 207. Okay, this is this beautiful picture, although one seems it's very difficult to read at the beginning, but then you can manage it with that. Okay, so you have a comparison with the large scale shell model and energy density functional plastic quark particle for model, and then you see that there is what is the structure of this state that are measured with the DP reaction. Okay, I will not give you more details because it's a kind of spoiling. I'm doing what the okay. The similar experiment has been done on thin 119. This afternoon, Michael will tell us that about these results. Here I show the picture you have already seen this morning. Okay, I will not go more. Another which is experiment done the same line was done at Legnaro. No, sorry, at LNS in Catania with tandem, and then they were analyzed with the Magnex spectrometer. They are still analyzing it. So these are very preliminary results for the spectra. Here you have, I don't know whether you can see here the stars which correspond to the contaminants. And eventually the idea is to compare all these results with the alpha prime on molybdenum 96, which is the nucleus which is analyzed with these two DP and PD experiment done at LNS in Catania. Okay, so I think we will have some answer this afternoon at the end of the week about this problem, whether the state can be considered collective or not. So now I go to the next point that we will we will consider as a problem, which is the interplay between isovector, isoscalar contribution. So the mixing of the isoscalar, of course, is relevant when you use the isoscalar probes. The quantity measured in this case are the inelastic cross-section. So it's important to have a good way to calculate this cross-section. We will see that the most important ingredient of this calculation are the radial form factor that I want us to use. Because I mean, since we are saying that the PDR are not collective, you cannot use the standard code where they use for the radial form factor the macroscopic model. So okay, these are two papers that I suggest you to read about the interplay between isoscalar and vector. These are comparison with the semi-classical quantum approach. So I said this already said it. So what is a way to calculate it is just related to what is called the time-dependent semi-classical approximation for the couple channel model. This is actually the first one to give a contribution to write down the couple channel, semi-classical couple channel model was Riccardo Broglia and the collaborators. Okay, so you are imagining that the two nuclei move according to the classical trajectory. When they get close, then you use the quantum mechanical to describe the internal degree of freedom. So you write the Hamiltonians, the sum of two Hamiltonian, where each one is formed by an Hamiltonian part, which describes the internal degree of freedom, and another one describes the excitation of the nucleus A, which is given by the mean field of nucleus B. The time dependence is through the relative distance. So you can write the time-dependent state like this in terms of this phi alpha state. And then the Schrödinger equation can be wrote in a set of linear differential equation in terms of this amplitude probability. And when you solve this one, you can calculate the probability to excite the state alpha, taking the amplitude probability at time infinity, and this is done for each impact parameter. And then the cross section, you just sum up, you make an integral of this probability for integrate on the impact parameter we have considered, and then you put it here transition coefficient, which takes into account all the process or the channel which are not explicitly taken into account. So you write it in terms of imaginary potential. So the most important part of this couple channel equation is this one, where here can appear the radial form factor. Of course, you can have okay. This will talk about the discussion. So the type of radial form factor you can calculate with many ways to do that. One is this, which I shall already quoted. This is the double Teller method for the isovector giant dipole resonance. This is a classical one. This is supposed that you are moving a neutron and proton one against the other one. So you get the transition density for proton and neutrons, the derivative of the density, and they are weighted with this factor in order to preserve the center of mass motion. Another way to do that is applying the hierarchical differing for the isoscalar giant dipole resonance. So you assume that the state is completely isoscalar, and then you can write down on a transition density for that. Then I will show you in the next slide. Or you can calculate what I call the microscopic form factor using the double folding procedure. I call it macroscopic because often you use a microscopic transition density. Say the transition density I can get from RPA, relativity RPA, QPM, and all these sophisticated mean field approach. So double folding procedure, I think all of you know this way of calculate the real part of the imaginary potential. You have an interaction, nuclear-nuclear interaction, which has also isospin part, if you wish. So you have an interaction between the nucleon here and the nucleon here, and then to get the nucleus potential, you have to integrate on the density of the two partner of the reaction. Or if you want to calculate the radial form factor instead of the density, you have to put the transition density of one side of the integral. Okay, I say one side because okay. Here you have the formula for the radial form factor. So this way to calculate the radial transition density or radial form factor is important because now I will show you. Because if you, for instance, make a comparison with what I've quoted already, the way to calculate the isoscalar giant dipole resonance, the transition density for the isoscalar, which is okay. The original work was done by Dill and then was corrected by hierarchical differing. So they assume that they have this pure isoscalar mode, and they assume that there is only one state to exhaust the energy Wilkinson rule, so they can write the transition density, which is in terms of the ground state density, the derivative of the ground state density. So this is the strength in terms of the energy, excitation energy, and the radius of the nucleus. So if you compare it with the calculate done with, for instance, for nickel 68, and you have compare with the RPA result, which is the continuous line, and the dashed line, which is the one of hierarchical differing transition density, you see that here at the surface there is strong differences, and this, if you calculate the form factor, you see that this difference is again at the radial, at the surface region. You have again this strong difference, and if you calculate the cross section in elastic cross section for the dipole low line dipole state in a reaction with carbon 12, for instance, 10 MeV per nucleus, you see that there is here in the forward angles, which are the angle important when you use this inelastic probe. So you have a difference which goes from 3 to 4, so which is important difference. So okay, this is something that I have said already. So since you have we can use there's a low line state as a laboratory for the interplay. We can. It's important to know the content of isoscalar and isovector part in the low line states. One way to do to estimate this was done by Parr and the collaborator. So this self-condensed relativistic quasi-particle calculation random phase approximation done on cerium 140 is the response isovector response for the dipole states, and this is okay. These are the region they have analyzed is between the 0 to 8, which is the radius of the nucleus, or from 4.25 to 8. And what they have done is just look at the transition density on proton and neutron, and for each particular state they've look at if they are in phase. If they are in phase of more than 70%, then they declare that the state is a state or is an isoscalar state with 7% contribution of the isoscalar part. So if you look just at the surface between 4.25 until 8, you see that you have the more predominant character isoscalar is concentrated on this part, which is the one that corresponds to the what we call the Pygmy dipole resonance. Another way to estimate the content of isoscalar part in these low-lying states was done by Xavier Rocamassa and collaborators. In this case, they use a fully self-consistent non-relativistic mean field with several three Scarmy interaction. These are the result for lead, thin 132 and nickel 68, and they've analyzed it in three regions, the full region of nuclear region, then from 0 to alpha the radius, and from alpha the radius until the surface. And in this case, they've analyzed for each radial distance when look at the transition density of neutron and proton, and that they find the state new isoscalar of 70% isoscalar if in 70% of the point analyzed they have these conditions. The transition density isoscalar is bigger than the one of the isovector. And again, the analysis showed that in the case of the surface, you have 70% isoscalar of the isoscalar state belongs to the low-lying energy peak. But also from the experimental point of view, one can also try to make something similar to see whether it's the content of the isoscalar content of the state. So they've Crespo and collaborator, well, most of them are here in the room, have analyzed that the two isotopes, zirconium 90 and 94, with PP prime at a reaction at 8 MeV and alpha alpha prime at 130 MeV. This was done in Osaka, I think. Okay, then the energy weight and sun rule, the isoscalar energy weight and sun rule, was extracted from the data obtained by the alpha alpha prime reaction. Then we may say we because I also I'm a co-author of the paper. We assume that the information extracted from the alpha alpha prime reaction can be extended to the PP prime reaction, the sense that we can use this the value that we have obtained from the alpha alpha prime and apply to the PP prime reaction. And in this case, we have found that the general trend of the cross section can be reproduced. So here I show for the two isotopes, zirconium 90 and zirconium 94, the data, which are these orange bars, these are the errors, and they compared with the calculation, cross-sectional calculation done for the Pygmy prime reaction, assuming that have the energy weight sum rule, the isoscalar part of the energy weight sum rule. So you went, I don't know. Oh yeah, now we can go. You have assumed that the one extracted from the alpha-alpha reaction are valid also for the Pygmy one, and then you find this. I mean, you can reproduce. I mean, you cannot get exactly the value of the measured cross section, but the trend you can reproduce, except for this this region here, which may be an indication that is. Don't have okay, have a different configuration, let's say. So this is a method that has to be of course modified and improved, but I think it may be a method also to investigate the content of isoscalar isovector in these low line states. Okay. As I said, but I will not give here any other details about that. Is just my impression, so probably we can discuss about that. It's the fact that the so-called isospin splitting, because I think at least a theoretical description of this phenomenon is not, to my point of view, completely satisfactory. Because okay, many calculation shown. I mean, in the experiment, sometimes, for instance, in thin 124, you have a very sharp transition between one region and the other one, and often in many other cases is like that. But the results of the theoretical calculation, one done by Elena or by Ponomarev or by Nadia, they have a very smooth transition. So this, I think, one may be interesting to work out from, I think, from theoretical point of view, because experiment is done, they are done in a very precise way. Although Michael advised us not to believe very much, but okay. So I think I can finish here. So the summary is that we know that these low-lying states have a strong isoscalar component, which makes them very interesting to study. Okay, so we have seen that there are a lot of open problems. Collectivity, isoscalar, the role of deformation. The role of deformation, we have a problem from theoretical approach. There are two opposite solutions, one Peter and collaborators, the other one from Yoshida, that they reach to different opposite conclusion. So this will be nice to see whether which one of them is appropriate for and then from experimental point of view, all very few experiments done for that. One is almost completely done in Itemba, and we'll see soon some work on that. And so this is what I have just said. So what is the message for the theoreticians? That we have to have a better knowledge of the composition of the low-lying states. It's already have done a good job in this case. We will listen this afternoon and Friday also about that. No, it's also another talk on a large model shell calculation, I think. A better description in the response of the form of the nuclei, as I said, and then a better calculation also for the inelastic cross-section, which, as I think I convinced you, are very important in the experiment when isoscalar probes are used. So this one, these are the collaboration of the pleasure to work with and along these years. And then I thank you for the attention. Yeah, exactly.
Microphone. So are there, Peter? Okay, go ahead.
Yeah, you added a lot of interesting things which are open. I would like to add another one. There, you went through the literature. Some people use SCRM, some people use relativistic. It's not really clearly investigated what is the influence of all these functionals.
I agree.
This is really a big problem which is open. And then it's a.
But
This could be done. The codes are around. This is just work. But on the other side, there's also a basic problem if you go to the form, you mentioned that, because the better thing you should do in this case, so close to the continuum, you should do a continuum RPA. And in spherical nuclei, it has been done, it's possible. But in deformed nuclei, it's a very open problem. Who can do a continuum RPA in deformed nuclei? Actually, RPA in deformed is already a big problem. There are very few calculations in very simple models, in very simple forces. So there's a lot of things to do which are interesting.
Yes, I agree. The point is when you do to make a selection of the Skirm force or Pygmy force that we are used, I think one needs, in this case, a very precise either experiment or a quantity where you can use to judge which one is it, which is not, I think, easy in this case.
Basically, no force.
Yeah.
Okay. Not doing RPA.
Yeah. Okay.
I like to add another aspect to this discussion, namely the unknown content of these multi-configuration mixing. So, I mean, all these RPA results rely on one particle, one hole, or two quasi-particle configurations. But if you look to our result, what we did, what Nadja did in Gießen and Vladimir in Darmstadt, then you have these mixtures of 4 quasi-particle configurations and even 6 quasi-particle configurations. And that is completely unexplored.
Yeah, that's right.
Thank you very much for your talk and the huge amount of information. For me as an experimentalist, it was very difficult to learn about what we should do. But helped me with in one thing. There are so many highly developed theoretical approaches to the problem. But a large fraction of your talk, you talked about the old Steinwedel, Jensen, and all these ideas. And so what was the reason? Are these old models, when I was a student, 50 years ago, are these old models still the only way to answer the question about the Pygmy and the giant? What brought you to do this?
Yeah. Okay. You can use this. Well, first of all, they were the first one to look at this low-lying model, lying states, because it was, I mean, in analogy, what was have been done for the giant dipole resonance. So it was the easiest way to approach that. So you have this very old paper where you have 3 fluids or this core. Then the other thing why I always say something about that is because the people that are not expert, colleagues are not expert on this field, the easiest way to explain what is this Pygmy resonance is to show this figure that of the of the neutron skin actually, which is not correct from my point of view, and I think many of us. But this is the picture that you can find in every conference. Everybody put this one,
including yourself. I mean, you
including
talked about
myself.
this, yeah.
Just, but myself, just to say is not correct. So it's just to correct.
So
that.
you confuse us.
Yeah.
You confuse
Yeah,
us
but I say
with an old
I say
model,
that it is
which-
not the correct. And then the other thing is that if you want to, that's also we have done with Andrea Vitturi. You have done a simple model to see whether and make a comparison with the RPA result. You just to see this inert core and skin neutron oscillate each one against the other one, write the transition density, write the form factor, and they compare with the RPA, and you see that they are different. Also this, but I didn't have time to show all the details here. So it was done for this.
I mean,
I'm
if
sorry
you
if I
take,
confuse you with that.
if you take Steinwedel, Jensen, and these other collective classical models as a guideline, then you compare it to these microscopic calculations, then you find these aspects are distributed over many of these microscopic states. So you get these classical models only if you average, so to say, over all those quantum mechanical effects and wash out the interference, quantum interference effects. And then finally, you're coming close to these classical old models. Yes.
These classical models are really important because all our understanding goes through the classical model.
That's
if
right.
you do a big calculation, I just mentioned linear, you diagnose everything and then nothing.
Yes.
So the understanding goes through the
Yes.
classical.
So to say, they give a hint to what you have to search. That I think
Although
that is
they
the
are not
most
correct.
important. Yes. Peter was first. Okay. Sorry, Peter.
Yeah, thanks, Achim. I would agree with what Peter just said. I mean, you need these classical models to see how much you actually deviate from that if you want. If you do truly microscopic approach, it's a bit. If you think back about the scissors mode, like starting from Nikolai Yudice and Palumbo's rigid rotor model of the scissors mode, which said that this mode should be there, but they predicted it's at 15 MeV or something. Then going down to real calculation, a microscopic calculation, which tells you where it is and what the strength is.
4.5 MeV, that took them 2 years to do it. And they got at the end, when we did the measurement, 4 months running the accelerator to search for it, it was then at 3 MeV.
Yeah. Okay, but I wanted to discuss one thing. I mean, you talked about collectivity, and you showed that there you can look at collectivity in the transition strengths. You can look at the wave functions, at least theoretically, also to some extent experimentally. I mean, I think that's the nice aspect about what you started that goes into this direction. I just wanted to point out that there is a third way, in principle, how one might test collectivity, and that's looking at the statistical distribution, for example, in terms of level spacings and other measures. Actually, many years ago, we actually attempted that also for the Pygmy resonance with the few data available at the time. And I'm hearing your talk, I'm wondering if one should get back to this with the much better database we have now. We did such an analysis for the scissors mode and showed that it's actually collective this way. I mean, that was very much debated because the strength is 2 Weisskopf units. And so people were arguing a bit like here, whether this is collective or not. But this showed it is indeed a collective mode. Actually, there are other things like the correlation with very collective observables like the deformation strengths. But what we did at the time was when we looked at the nearest neighbor spacing distribution, we got something which was intermediate between, let's say, a Poisson and GOE prediction. And the problem experimentally is, one must admit, you always must make sure you have the full level sequence. That's
That's
maybe the difficulty. I'm not sure how prohibitive that is for this kind of analysis, but in principle, it's an independent way to check that.
okay. Thank you.
Yeah, but you need to know the weakly excited states as well for such an analysis, and that is, I think,
some corrections for it,
yeah.
but the question is how many are you missing?
Mark, you are next.
Comment on that, but I'll have another question or comment. Thank you very much, Edoardo, for your talk. I think it had one very, very important aspect in it. And Professor Peter commented on that as well. As we are going more and more neutron rich, especially now with EFRIT being operational, hopefully FAIR becoming operational at some point, the continuum becomes important. Yeah. And so we have to understand the intersection of structure and reaction much better. Because what we experimentalists are measuring at the end of the day are cross sections, right? And then to really compare to the microscopic foundations of these cross sections, we need theory input. And one way is that you showed to use these microscopic transition densities, form factors, use a double folding approach to calculate the cross section and then compare to the experiment, right? And maybe you can go back to that slide because that's where my real question comes in, where you showed the 68 nickel carbon 12 and the two cross sections that you had there.
One is that again?
When you talked about the Catania measurements on 68 nickel with carbon 12. Yeah, and at some point you showed the predictions for the cross section, the differential cross section with the energy. So further I go, you have to go forward. Sorry.
No, it's okay. The point is I cannot. No, okay. That's better.
Further down, further down, further down, further down, even further. Yes, that one.
This one.
Yes, yes, that one is. All right. So now in your last figure on that slide.
Yes.
You have the differential cross section, right?
Yes.
And the shape looks similar, even though the scale or the predicted cross section is different depending on which form factor you use.
Yes.
Now, this connects to my question of saying, okay, experimentally we measure cross sections, right? But if we compare to theory, there's always a scaling factor. So if you take traditional DWBA, those are your deformation parameters, the betas or your deformation lengths. And also in Fabio's work, right? When then going to the experimental cross-section and showing your comparison for the two zirconium nuclei that you have there, there's always a scaling factor in there. So the shapes look very much the same, and there are experimental uncertainties like the opening angle and others that contribute. So that would be contributing on the x-axis, and then statistical uncertainties or systematic uncertainties in the determination of the cross-sections on the y-axis. How significant is this difference really? While you still have to do a scaling at the end of the day.
No, okay. The scaling is done for the isoscalar energy weighted rule, because okay, you assume the first calculation you do is with the isoscalar energy weighting rule given by the RPA or whatever microscopic theory use. This is the one which usually is not correct because you have some difference always. I mean, it's very difficult to reproduce exactly the experimental part. So that one is that you use just to scale in order to have you increase or decrease the fraction of the energies weighted sum rule to see whether the cross section is equal to the experimental one. The point that I show here is that the difference that you have at the forward angles, it's a factor 2 or 4, 2 or 4, yes, between 2 or 4. And this is maybe a problem when you try to extract from the cross section the energy width. That is my point. How good is the calculation? Because this was your question, the calculation to compare directly to the experimental. Okay, this it's within this if you wish, this factor. I don't know whether the point is that you use the macroscopic isoscalar gender resonance, and you are sure you are missing the cross section of this factor. This is the main message. So if you use the macroscopic form factor, you are sure that you have, in a sense, the right description of the mixing, because otherwise you are assuming that these are, which is true. I mean, because among all the states that you have in the low-lying peak, you have some of the states which are pure isoscalar, but most of them are mixed. So my message is this one, that it's better to use the form factor that describe you these mixings rather than use the isoscalar one. I don't know whether it's
in the ideal world, you should use the theoretical microscopically calculated form factors, transition densities, and then compare to the data. And then you know whether the theory is good enough or not, period. And
state by state analysis.
State by state, sure. And that is quite involved.
And then the other thing that you can do all this calculation. We have done a calculation with with Elena and Nadia also.
I also want to encourage the remote listeners to ask questions if there are any. And so don't hesitate to switch on your.
So I would say that only using this semi-classical approach, you are able to do the calculation for these thousands of states. With the Fresco code, you can renounce that.
So you have to design a particular code adjusted to the microscopic input.
I had a question about, you discussed one example of, I mean, there are various data sets, also not much is published yet, where alpha prime gamma and pp prime gamma at energies low enough that you basically have nuclear excitation only are compared, and what we eventually can learn from that. I mean, one of the arguments to do this were that it was said that you probe a different range. I mean, it's both surface reactions, but still it was argued that with the proton, you really assess a slightly different range of the transition density. And I would like to hear your opinion about that. But my question more specific was, you showed that you analyzed the alpha scattering, extracted the strengths, and then you put it in to calculate the proton scattering cross sections. Wouldn't it be an alternative? I mean, for the proton scattering, you have pretty good effective interactions, proton-nucleus interactions, which you can again combine with your microscopic input and directly calculate the cross sections. And then, okay, if you can make the assumption that you have to make some assumption of scaling that if you scale that with a factor, then you also have to scale the theoretically predicted strengths. Wouldn't that be an alternative for this kind of analysis?
Well, yes, an alternative and a way to check it whether it is working. I mean, if the assumption that the information that you get for the isoscalar energy weight tension rule for I mean, one of the two reaction is true also for the other one. So this will be a double check. I think it will be nice to do that. And you know what I mean? I mean, you have to do, if you do the both ways, you take from alpha and then make a calculation for PP prime, or as you suggest, you make the first you extract as a vector energy Wilson rule from the PP prime and then using the alpha, and then in principle, if your hypothesis is correct, they should be very similar. Yes. Yeah, this will be a good check to them.
So last question by Elena.
Thank you very much for comprehensive talk. I wanted to ask you about the transmission coefficient. You mentioned that
the cross section.
Right.
Yes.
So
Before. Yeah.
You were saying that you need this transmission coefficient to take into account processes which are not explicitly included. So
yes.
Could you please give some details
Yes.
of this?
So the problem is that this semi-classical approach. You have you calculate the amplitude. This amplitude, there is a probability for each impact parameter. Each impact parameter, you make a collection for 100 of impact parameters. Then you reach a point when you have grazing collision, or you may have a very, let's say, head-on collisions. In the head-on collision, you know that there are a lot of other channels that take the flux away. So these are you have to take into account. So you have to consider only the contribution close to the surface of when you have a grazing collision. And a way to do that is to run several run for each B, and for each B going to check which distance they have got. We are talking about classical motion in this case, which distance they have reached, and so on and so forth. A way to do it in a global way is just to put this transmission coefficient, which is just a way to say that as soon as you reach a certain region, then all which will be absorbed. So we will not have any contribution. So that's why this T is written as an exponential of the imaginary part of the optical potential. This will guarantee you that you are not taking contribution from the how do you say, inner part of the nucleus, which is.
And where do you take this optical potential from?
The optical potential is in a case where you have information about elastic cross section, then you can extract it from there. You construct the real part with the double folding procedure. You take the two density of the ground state density of the two nuclei or the partner of the collision. You make the double folding procedure, and then you get the real part of the optical potential. For the imaginary part, you may have the information on the elastic scattering, and then you get information from the experiment in the sense. In case where you don't have this information. What we use is a kind of, we call it a standard procedure, which is accepted by almost everybody, which is just to take the same geometrical shape of the real part, which means the double folding procedure, but with half the strength. This, of course, will not guarantee that this is the correct optical potential, but in many cases gives you reasonable results.
Yeah, I was just thinking that perhaps we could provide microscopic optical potentials from the same model, actually, because this is in principle possible.
Yes.
So if you are interested.
But in this case, it's it's what the optical potential that is because you mean you make the calculation with putting all 1 minus 3, 2 plus,
yes,
3 minus,
exactly.
and all these states.
Yeah, just
and then
from the
you take the
self-energy.
calculation of all the other states except the 1 minus, because the 1 minus you put it explicitly.
Yeah,
so
it could be done consistently on the same level as we provide.
Okay. Well, that would be nice.
For the transition test.
Yes, that
Yeah.
would be nice.
Okay, we can probably discuss it later. Thank you very much.
Okay, thank you, Edoardo, and thank you all the speakers of this morning. And